favorite song, the one that makes me go all night long.
Now, our general session is meant to demonstrate ways in which disruptive innovation can be used by our industry to help us reach our possibilities and grow the industry. We have 3 speakers that have done all just that, but for different reasons and different ways. They are all accomplished and inspiring in their own way, and I now look forward to learning from each of them.
Please welcome Kurt Jordan, Oracle Team USA designer.
Hi, good morning. I guess I'd like to start by thanking CAMX for inviting me here this morning to talk about really my favorite subject, which is the America's Cup. So we'll get right into it. So the America's Cup is the oldest international sailing trophy in the world. It's been around for 166 years. I'm going to go through just a minute of history for those of you that don't follow sailboat racing. So what is the Cup? Fundamentally, it's that trophy that you just saw and a 2-page document written in the 1800s that governs the competition about that trophy. Like I said, it's 166 years old. It's the playing field for industry titans since before the Civil War. J.P. Morgan, Larry Ellison, or the likes. It's primarily a sporting competition with very athletic sailors and seamanship as a major component of it, but technology is also a huge part of the America's Cup yacht racing. That's what I'm going to touch on this morning. An America's Cup campaign is typically about 3 or 4 years, and for the larger teams, budgets of $100 million plus are very common, so it's not for the faint of heart, as you can imagine. And that leads to something that excites me a lot, as it makes my job really fun. We have a short cycle time, and we're judged by the performance at the end of 3 years, so we're pushed to develop things in a very rapid pace, and which can be pretty stressful, but pretty exciting as well. Just a little bit of background. Primarily, the hulls are built out of pre-preg carbon fiber sandwich panel with honeycomb cores. So we'll touch on this a little bit more, but that's just a little backdrop to the primary hull construction. So one of the themes of this morning is disruption. And I have to tell you a funny story. Is when my wife asked me what I was going to be talking about, and I said, well, the America's Cup and disruption. And she laughed and said that it'd be really easy for me because it's disrupted my life for 27 years. So the America's Cup, in my 10 years, disrupted the composite industry, or led it in some areas that I think are really interesting. And on the converse, the America's Cup has really innovated and disrupted the sailing world in some dramatic ways, which could only really happen with the aggressive use of composite technology. So I'm going to talk about each of these just very quickly. So in 1992, the winner of the America's Cup built their yachts in a large autoclave in Utah. And it was very expensive, and a technology the size of the autoclaves was not accessible to most of the teams. So the America's Cup community came up with a rule that outlawed the use of autoclaves for the big hull structures. So we went headlong into figuring out how to process big composite structures out of autoclaves. So we're talking about 75-foot hulls with about 2,000 pounds of composites in it. And there were some dramatic failures as we learned this, but some great successes. And by 2000, out-of-autoclave processing was the mainstay of performance yachting as it is today. The coined phrase out-of-autoclave wasn't even used then, but it was processing elevated temperature pre-pregs under vacuum pressure. So I like to feel like the America's Cup was at the lead of that. And if you look today at the CAMX program, or any program from CAMX or SAMPE for the last 15 years, you'll see technical papers on out-of-autoclave processing. So I feel a bit smitten that we were kind of helping lead that whole process. So here's a beautiful picture. This is Bermuda last summer. What you have on the left there is a J-class America's Cup yacht, and those were the yachts that they used in the 1930s for the America's Cup. And on the right is our race boat for the 2017 America's Cup boat. So you can see kind of 80 years of progression there in the style of boat used in the America's Cup. This graph, I love this graph. If you look at it, the bottom left, so Cleopatra, a few decades before Christ, was sailing on the Nile at 3 or 4 knots of boat speed. 1,600 years later, Columbus sailed across the Atlantic on an average speed of less than 3 knots, but 4 or 5 knots of boat speed. The 2 yachts you saw in the previous picture are highlighted there. In the 1930s, those boats were racing around the race course at kind of 10 knots. Last summer, we were on the race course at 48 knots and above. So that's, for you non-sailors, that's 55 miles an hour in a sailboat. So it's really cool kind of technology. So if you wanted to look at a graph of disruptive technology, there it is in the sailing world. So what does this look like? Here's just a quick little video of our boat training in Bermuda last summer. And a couple things to note here, look at the water. It's not really very windy. It's probably 10 knots of breeze there. And this boat is lifted up on foils and is sailing above the water. When it's going upwind, this boat goes, in these conditions, a little bit more than 2 times the wind speed. And when it's going downwind, it's over 3 times the wind speed. So in these kind of plastic conditions, this boat will go over 30 knots. So just really, really neat technology. Pretty much everything you're looking on this boat is pre-preg, carbon fiber, kind of advanced composite technology. So I'm going to highlight just one little piece of this boat, just so you have an idea of what we're doing with it. And it's the structure called the dagger boards, which are these L-shaped foils that drop down into the water, allow the boat to lift up out of the water. So really the whole boat is leaning on this foil. So these dagger boards have a lot of conflicting design parameters. They want to be as stiff as possible, they want to be as light as possible, they want to be as thin as possible, and they can't break. So a lot of conflicting things that go into the design process. So I'm just going to highlight a few of the things that go on with these boards for interest. So there's a couple of things that most of you probably know in this room, but a couple of characteristics of carbon fiber I want to point out as a backdrop. One is there's a lot of different grades of carbon fiber, and typically as you go up in stiffness of carbon fiber, the material becomes more brittle. Another characteristic is carbon fiber laminates are typically much stronger in tension than in compression. So these dagger boards that we're flying these boats on have one side that's dominantly tension, which is the top of this cross section. So we use a high modulus fiber as much as we can on the tension side of this, and those cured laminates are a little better than the stiffness of steel, but less than 1/5 of the weight. Then on the compression side, we have to compromise. We use the high modulus carbon fiber as much as we can until the strain levels get too high. Then we need to switch over to an intermediate modulus fiber that's up for the job of the kind of maximum strains the compression side sees. So just a really cool use of composite materials and something that you couldn't accomplish with any other kind of material. So another kind of neat thing that we do with composites in these dagger boards is use very asymmetrical laminates, and primarily in the horizontal wing, the part that's lifting the boat out of the water. And the laminates will dominantly be 0-degree fibers like the yellow cartooned out there, but with one other dominant fiber angle, like for example, +15s. And what this does is it develops a laminate that has coupling between bending and twisting. And where this feature comes in is these dagger board wings are quite long. One of the design trade-offs is we want a dagger board with a lot of lift to get the boat out of the water soon. But once the boat is out of the water, the speeds go up dramatically, and we don't need nearly as much of that dagger board working in the water. So what happens as this boat lifts up is that the load comes onto that wing, it bends up, and it twists, reducing the angle of attack as it gets out of the tip, making the tip more neutral in the water, reducing the drag profile of it. So just a second example of some of the really cool stuff that only composites allows you to do within structures. So what's next? The concept for the next America's Cup was released about a month ago, and here's a little animation of the style of boats that we're embarking on for the 2021 America's Cup. And keep in mind, these boats are 75 feet long, about 7 tons, and all of the predictions are they'll be faster than those catamarans that we were sailing around last summer. And one of the things, these boats are not reality yet, and there are big design teams with all the America's Cup teams kind of mounting their soldiers to figure out how to make these boats work. So whether or not you're a fan of yachting and watch racing, if you're a fan of kind of aggressive use of composite materials, I recommend that you might want to watch what happens in the America's Cup in the next 3 years. And that concludes my remarks. So thank you very much for letting me talk about the America's Cup.
Please welcome James Antonic, Composite Building Structures.
Good morning. Thank you all for coming. My presentation is about thinking. Do fish think? What do you think? We've all been accustomed to thinking too much, too often, about too many things. Is there a commonality among animals? What are the major differences? These were some of the questions when I studied experimental psychology at university. Looking for answers, I went one night to the Chicago Playboy Club to conduct field research in the lounges. Seeking answers there, and was enamored by one of the acts. They called him Professor Irwin Corey, and he told about his experiment to answer the question, do fish think? His conclusion then is even more relevant and compelling today. And that experiment started my path to assemble housing in all countries. His experiment used a large fish tank he called the environment, and the fish food he called the resources. At the end of each feeding tube, there was one called tradition on the left side, and the other he called the disruption on the right side. Each day he added more fish to increase the populations and fed only through the left side traditions, and began diminishing the amount of food each day until one day the food entirely stopped. On that same day, he started to add food through the disruptor tube on the right side and watched the fish as they got more agitated and more hungry. They never abandoned the traditions tube, and very sadly, slowly, they starved to death. That ended his experiment and answered his question. Yes, fish do think, but not fast enough. Professor Corey's findings were based on his background and his thinking, just as yours are and as mine are. All of us have different backgrounds and the thinking, but ended up in the same industry. My background started as a foundry laborer. Later, in iron and steel and non-ferrous casting foundries, that supplied the car, truck, tractor, and engine manufacturers. In those foundries, I studied how to stop defects in castings, and later, with the foundry chemical supplier, Delta Oil in Milwaukee, was hired to help me and them get their distributors how to solve all of the defects in castings. I began teaching that in several states. I ended the foundry career by establishing licensees to make those companies' products and started them on training in Europe and Asia. I still find it hard to believe that laboring in a foundry could develop an international career by speaking only the English language and foundry words. Then came composites. They opened a whole new world of possibilities and put me on a track for reducing risk in businesses by replacing traditional materials with composites. The interesting parties for that concept would be insurance companies, homeowners, and corporate investors once they learned how they were significantly better, made better. Pultrusions were stronger, safer, lighter, and greener than all the other materials in use. I started working with a foundry licensee in Japan who insisted that they build tiny homes as luxury cabins in mountain resorts as fully contained modules on steel frames so that they could tow them around the narrow, curvy roads. We consolidated special wood and steel materials for them, packed them in containers, and exported. When I first saw a pultrusion framing, it was a set of over 26 individual pultruded sticks that built a do-it-yourself structural frame. Composite parts would be much better if re-engineered in just a few parts and assembled on a production line. We simplified production line elements and applied them for house paneling. This jig supports a worker on each side of the trapezoid's 2 assembly lines. Now, architects draw the plans and elevation, and engineers turn those plans into individual disaster-resistant panel sections, securing pultruded studs with the stainless steel screws. Houses in the United States were still primarily built one at a time in series. What I learned in the foundries and assembly lines was in a completely different universe. Other universes assembled high-quality products in large quantities, economically, but not in America. How was assembly line building accomplished? Well, Henry Ford started the first assembly lines and became a standard throughout the world. But this technology never impacted home building. So we started at a team and a company called Composites Building Structures to assemble and erect buildings anywhere there was a deficit, and such innovative thinking might disrupt traditional building methods. We designed all tasks on the lines to work with hand tools, manually. The jig verticals were aligned, and the studs were matched to them without measuring any of the separations. Precision parts were pre-cut to length and drilled with holes for the electric channels and water piping before they were received. That eliminated the cutting and measuring in the plant. Assembly stations added all of the connections, sheeting, and insulation inside the panel core, while wall surfaces were attached with pre-finished and interior sheets or exterior sheets. Also, those were cut to measure. In support of the assembly plant, the team continued developing and developed ancillary manufacturing processes to manufacture fire-resistant insulation, bio-insulation, roofs that took the heat from the sun and converted it to electricity to power the entire building with low voltage appliances and to become energy independent in each building. The team was able to use these same lines to produce many styles of buildings. In all cases, they started with a bare bones model and installed a wide variety of options as they assembled. This was the same method that the car makers used to add features to their cars online. In the case of composite building structures, homes and other buildings to be constructed only needed people power instead of the machines. Panels are assembled with battery-operated screw guns, erected on foundations with anchor bolts, and joined as complete walls with the same battery-operated screw guns. We designed this system to rely solely on manual labor so that it would be set up and could be set up in any country with need, and identified suppliers in several countries with different pricing levels. These methods were designed to counter deficits in all countries with local designers made just from 6 pultruded lightweight shapes. We found a great building need existed globally, along with a need for also providing higher paying production jobs. Globally, these were great opportunities to improve lives, upgrade communities, and add new taxable bases to the local governments. This structure could then be licensed, set up, trained, and started in an empty building or between 2 rows of containers, hopefully they're also made of composites, stored in the assembly lines would be the parts and inventories. Everything fit into slots in the protrusions so that the entire wall panels and sections could assemble any type and style of building. The completed building systems had become a fully operating system. These patents were granted to both the utility functions and the design functions, and all with hand labor. These developments also resulted in our team's solutions for the world's housing deficits. To rely on only manual labor set up in any country with building needs, supplies sourced from around the world, and prices changed based on the logistics. This was a complete business, a structure designed to be able to match the variations in local building designs and construct them from the same 6 pultrusions. This was a marketing plan designed to be duplicated, licensed, and set up around the world with training and supplied with ongoing consulting. It would start in any building or between 2 rows of containers and eventually serve and work on solving the world's building needs. We wanted to help solve deficits and thought passionately about the way to do that, to improve necessities in markets and their local economies. It was possible to greatly lower costs and provide big opportunities and generate more money in all cases by partnering with them in country. We could together begin to solve the pockets of poverty, squalor, and hopelessness prevalent in their economies, problems that I had seen traveling around the world in the foundry business and assembly line businesses. We decided to do something about it and change the paradigm with a simple change in the approach. We needed resistances, and that became the structure that we were putting, but we had to now begin to convince the industries, networks, people, and media that we're going to build those things in other countries, because at the end of the day, it's still the only world we've got, and we must use ways that take care of it when meeting those challenges that we all face together. Thank you.
Please welcome keynote speaker, Kerry Manning, Boom Technology.
Hello, my name is Kerry Manning, and I'm an Aerostructures engineer from Boom Supersonic. I started my career in 2001 designing composite wing structures, moved on to leading wing and fuselage structures through FAA certification, became a DER, and 2 years ago, I joined Boom to design the wing of our new aircraft. Boom is a startup company based in Denver, Colorado, where we're designing the next generation supersonic airliner. Today, I'm going to tell you a little bit about our aircraft and how today's technology is enabling us to disrupt the commercial aircraft industry. For those who don't know about Boom, I'm going to show a short video that'll tell why we are tackling such a big engineering challenge, and then I'm going to dive into the details of how we are doing it.
The pursuit of speed is often relegated to the adrenaline seekers, the risk takers, the record breakers. But our pursuit of speed is about something greater. It's speed in service of the experiences that make life precious. Imagine, if you will, flying across the Atlantic, doing business, and being home in time to tuck your children into bed, or where New Zealand becomes as accessible as New York. What would that do for families, for culture, for business? The technology for supersonic flight has existed for over 50 years.
Is the new supersonic airliner.
But it was too expensive for routine travel. At Boom, we are refining it, perfecting it, so that high-speed travel can be available to anyone. In the digital age, there really is no more distance. There is only time. Time from one another. Our mission is to remove that barrier, meaning more meetings in a day and more nights with loved ones. Where children grow up with their parents at home, and where relationships are no longer considered long distance. We see New York to London in 3 hours instead of 7. San Francisco to Tokyo in 5 hours instead of 11. We see world leaders spending more time in the same room, the acceptance of cultures, and the spreading of ideas. At Boom, we see the time saved is really the least important part. This isn't about time saved, it's about life gained. Together, we can make cities into neighborhoods and make the world a smaller place. Boom. The future is supersonic.
For me, watching that video, I can tell you that from my own personal experience, I wish supersonic flight was available today. I used to work for a large corporation over in Europe, and I would fly over there routinely, sometimes for a week, sometimes for a few days, some cases a 3-hour meeting. As a result, I spent many hours slowly crossing the Atlantic Ocean. When I'm sitting on a plane for 8 or 12 hours, I'm not thinking that I wish I had a better movie selection. I really wish I was home with my wife and kids. This map shows all of the routes where the boom jet can operate profitably with ticket prices that are competitive with today's business class. These 500 routes were determined based on today's volume and fares, and an independent analysis done by the Boyd Group has shown the potential for 1,300 aircraft over the first 10 years of service. Now, when I introduce most people to boom, the first thing they think of is the Concorde. Some people go as far to say that the Concorde tried supersonic flight and it failed. So, what about Concorde? Concorde was an amazing aircraft and had a very good safety record, but it was a government program driven by national pride, not a sound business case. This led the Concorde to be a technological marvel, but not a business success. For a variety of reasons, the Concorde had very limited production and routes. Furthermore, it was an aircraft designed in the 1960s. It's an airplane that first flew 10 years before even I was born. We all know that commercial aircraft that we fly in today are much more advanced than those 50 years ago. At Boom, we believe that there are 3 main technologies that enable us to offer cost-effective commercial supersonic flight: engines, composites, and computers. Being as CAMX, I will always be focusing on composites, but I'll also be touching on the disruptive power we have in computing power today. Being an aircraft in the 1960s, the Concorde was constructed from aluminum, which presented a unique challenge at flying at Mach 2. You see, when you fly supersonic, the air around an aircraft heats up. When you go above Mach 2, it's about 300 degrees Fahrenheit, or 150 Celsius. Because of this, the Concorde had to be built with a specific special aluminum alloy that would retain enough strength at temperature to be viable. But even this special alloy was at its limit. If they wanted to fly faster, they would have had to use stainless steel or titanium, like the Valkyrie or the Blackbird. Regardless of the type of aluminum used, it has a very high coefficient of thermal expansion. So high that the Concorde would change in length by about a foot in flight. This expansion and contraction would happen each flight, and even worse, different parts of the airplane would expand and contract at different rates, making that design challenge even more difficult. This required a lot of complicated connections and parts. I was surprised to learn how much of the Concorde was actually made from machined aluminum as opposed to sheet metal because of this reason. Obviously, this added significantly to the Concorde's weight and cost. Of course, that was a half century ago. Fast forward 50 years, and aluminum is being replaced by composites. The majority of civil aircraft these days are composite, from the big Boeing 787 and Airbus 350, down to the small general aviation Cirrus aircraft. Composites are the answer. I think here at CAMX, we're all familiar that the fact that carbon fiber has great strength and weight advantages, but that is even more the case at higher temperatures. At Boom, we primarily use Tenkate's TC350, which is an out-of-autoclave epoxy material that has excellent strength retention at elevated temperatures. Now, this isn't some highly specialized formulation, but rather it's an off-the-shelf commercial system. Being a commercially available material, we avoid the risky and time-consuming process of developing a new system. This gives us an available, cost-effective system with significantly better properties than aluminum at elevated temperatures. If I can go that, oh. And it's not just the fabrics and resins. Adhesives, cores, and sealants have all been selected and tested to perform in this environment. For the past couple years, we've been performing coupon, subcomponent, and component tests on the material systems. Obviously, we've been performing many of these tests at elevated temperatures. Here's one of our latest tests. This is a spar that we heat soaked to 300 degrees and then applied bending moments to failure. Now, I mentioned the 300 degrees temperature due to Mach heating, but this doesn't include the heat from the jet engines. This additional heat can raise the temperature inside the nacelles to well above that of an epoxy system. Luckily, we have cyanide ester systems that are available like Tenkate TC420, which is an out-of-autoclave system with a TG in excess of 650 degrees. So we can use this instead of heavier and more expensive stainless or titanium. Finally, in addition to strength advantages, carbon fiber has a very low thermal expansion. With carbon fiber, that 1 foot that I mentioned earlier is reduced down to about an inch. Also, composites allow us to make pretty much any shape that we want. Concorde was well known for its beautifully shaped wing, but its fuselage was a constant cross-section. This was done for manufacturing reasons, and it was an aerodynamic compromise. Composites allow us to design the aircraft to be what we need it to be. With composites, we are free to take full advantage of what is known as area ruling to get the maximum efficiency from our design. To decrease wave drag, we actually have the front portion of the cabin significantly taller and wider to reduce drag and lower fuel burn. As a bonus, it also gives us a larger, more spacious cabin, improving the customer experience. Now you may ask, how do we know what the optimal shape is? Well, the answer lies in the other technology I mentioned, computers. In the 1960s, the Concorde was designed with the drafting table and the slide rule. And it's pretty frankly amazing what they had done with that. But when they wanted to evaluate an aircraft configuration, they had to build physical models and test them in a wind tunnel. This could take 6 months and millions of dollars. But today, everyone has a smartphone in their pocket with vastly more computing power than was available to the entire Concorde program. So at Boom, when we want to design our aircraft for drag or stability, we do it virtually. Not surprisingly, we highly leverage computational fluid dynamics. CFD allows us to virtually test the aircraft. We don't need to wait for a model to be tested, as we can generate and analyze different configurations in a matter of hours. And thanks to today's cloud computing, all we really need is a laptop and an internet connection. All that being said, we don't just have blind faith in pretty plots that are output from the computer. We still do wind tunnel testing. It's critical to validate our design and mitigate any risks before moving on to full scale. This incremental approach is essential to avoid any surprises during our flight test program. If we can go back one. In order to maintain supersonic cruise performance, high alpha vortex lift is essential to maintain low landing speeds. This type of behavior is much harder to analyze with CFD when compared to traditional attached laminar flow. So this is where we have focused a lot of our testing effort. We use this data to validate our models. Using CFD isn't new by any means, but the cloud computing is a game changer for small companies like us, where owning and operating our own resources isn't efficient or practical. Now, I've been talking about incremental and testing and validation approach, but we are taking that much further than just the lab. Our first product is a 55-seat commercial aircraft, but that's not the first aircraft that we are building. The wind tunnel testing I've been showing is for our 2-seat demonstrator, the XB-1. It's being built with the same materials and will give us invaluable data on performance, handling, and critical systems. This 1/3 scale aircraft will be used to test and validate our design and analysis methodologies before we finalize our much larger and much more expensive production airliner. I've talked quite a bit about how we can design and iterate on our design very quickly. One of the things that I do at Boom is the lofting, which is the design of the external shape of the aircraft. In the past year and a half, I've made about 500 detailed models, and the Aero team has performed thousands of more parametric CFD runs, all in the quest for a safe and efficient aircraft. We can iterate through multiple designs in a single day. The end result is that we can optimize an aircraft shape to minimize drag. This is what allows us to deliver Mach 2.2 flight with the same fuel burn as a conventional business class seat. As you can see with this rendering, Japan Airlines is the latest airline to sign up for the Boom Jet. Just last week, we were happy to announce that not only have they taken options on 20 of the aircraft, but they're also investing in Boom. Having flown from Tokyo to Denver, I can say I look forward to making that trip in half the time. Finally, I'd be remiss if I didn't take the opportunity to say that we are actively hiring the best and the brightest to join our team. I do have to say, one of our fellow structural engineers offered me 1 bottle of my favorite beer for any candidate who applies with hypersizer or bondline in their resume. So please, if you are up for a challenge and want to do something that will change the world, please go to our website and apply. And with that, I'd like to thank CAMX for inviting me out, and I hope that I was able to show you how composites are enabling us to disrupt the commercial aircraft industry and make the world just a little bit smaller.